Hey guys, Mr. Backward here. In this video we're going to look at using regression to model population. In this first example we're going to look at modeling the US population using exponential regression. So we've got a table of values in here that represent given years and the US population in millions of people. Now in our calculator, when we're looking at our X values or our list 1 values, we're going to let X be the years after 1900. So 1900 is going to correspond with an X value of 0. 1910 would be an X value of 10, and then 20, and then 30, and so on down the line. So I'm going to use my calculator, and I'm going to type in these years in my list 1, and I'm going to type in my population in my list 2. So in my calculator, I'm going to hit my Stat button. I'm going to edit my lists. In my list 1, I said I was going to put the years, starting at 0 and counting up by 10. In my list 2, I'm going to enter in the corresponding populations. Now that I've got my data entered in, I'm going to hit my Stat button, go over to Calc, and we're going to do Exponential Regression. So that's this EXP reg, that's Exponential Regression. I hit Enter. I entered my X values in list 1, my Y values in list 2, so that information is okay. So I'm going to go down to Calculate and hit Enter. So it gives us a Y equals A times B to the X equation with our A value listed and our B value listed. So if we think about that population model, our function would be P of T equals, now I'm going to do a little rounding, but I'm going to carry quite a few decimals in here just to make sure that I'm getting exact values. So I'm going to go 81.2263 times 1.0123 to the t power, since we're talking about time. Now this function is a pretty good fit for the data that we're given, so we can use this to do a little predicting. So say we wanted to predict the population in the year 2016. Well, first we would have to find a t value that corresponds with the year 2016. If 2010 was 110, then 2016 would be a t value of 116. Now if I want to do this predicting, then I'm going to use my calculator to help me out. So I've got my population model typed into my calculator. I've also turned my scatter plot on. So I'm going to do zoom 9 to automatically adjust my window for this data. So we can see that our data is pretty close to our model. Now if I want to predict for the year 2016, I'm going to hit trace. Now notice it's saying that I'm on my plot 1 with my data from list 1 and list 2, but if I hit my arrow up, then it's going to move to our Y equals equation. And if I want to find a specific X value, then I can just type in the X value that I want. So I want to look for an X value of 116, since that means the year 2016. And when I hit Enter, it'll tell me that my Y value is 348.33 approximately, which corresponds to 348.33 million people as far as the population in the year 2016. So for the year 2016, we predicted that the population would be about 348.3 million people. Now if we look at the actual census data for the year 2016, the population actually was 323.1 million. So we've got a little bit of an overestimation by about 25 million people. And the reason that happens is because exponential growth is unrestricted, but population growth is not. A lot of times there are limiting factors such as available land or available resources, so eventually population growth needs to slow. So exponential growth models aren't always the best when we're talking about population. So in this example, we're going to look specifically at Florida, and we're going to model its population using logistic regression. Now, similar to the last problem with our years, for our X values or our T values, we're going to let those years represent the number of years after 1900. So 1900 is going to be 0, and then 10, and then 20, and so on down the line again. And to do this logistic regression, I'm going to use my calculator. So if we plug in those values, then we end up with this population model down here on the bottom. That's our logistic model. Now, if we remember with logistic functions, that C value on top is kind of like the maximum value that we're ever going to get to. So our population is never really going to grow above 26.697 million. So we can actually look at this as a limit as we're going out to the right-hand side. So as x approaches infinity, then we're actually going to have a horizontal asymptote happening at that 26.697 value. So we can consider that to be the maximum sustainable population in Florida. So that means that's about as many people as they have room for and resources for. Now we can also look at this graph on our calculator and compare it to the data that we had entered into our lists. So I've got that population model typed into my calculator, and I've got my scatter plot turned on. So I'm going to do zoom 9. Now right now we can't really see our logistic model flattening out. So I'm going to extend my graph further to the right by hitting that window button and making my x max go up to 200. Now we said that our limiting value, or our highest value, was going to be just a little bit more than 26. So I'm going to make my y max go up to 30. Now when I hit graph, I can see my graph following those data points, but eventually with this logistic model, the population has to start leveling off, so that means that it's not increasing quite as quickly. That's going to be it for this video. Thanks for watching.